Hello, good afternoon to all of you. My topic is rare events and aggregation. This is just a general overview of the work that we have been doing. This work we are doing this work with my supervisor R. Rajesh, Oleg Zabronsky and Rahul Dandekar. Okay, so cluster aggregation. It is a phenomenon where you have two clusters of different masses which come together and aggregate to form a bigger mass with some certain rate. And this occurs in many physical as well as experimental setups. Processes where it commonly occurs are clot formation. When we get a wound and the wound heals, clots form, and aggregation is a mechanism of that, involved in that. Another example is the aggregation of dust, gas and ice particles in Saturn's rings, in planetary rings basically. And this is actually a data from this Voyager spacecraft of the mass distribution of the clusters which have been found in the Saturn ring, compared with some analytical results from a model. Okay, so what are rare events? These are events which basically occur at the tails of a probability distribution. That means that they occur with very low probability, they hardly ever occur, but then when they occur they may have a significant impact, so it is important to study it. Some common examples are natural disasters, financial stock market crashes, etc. So then why study rare events in aggregation? Just to motivate why in aggregation. So this is the picture of what happens in the brain when one gets neurodegenerative diseases such as Alzheimer's disease. This is actually for Alzheimer's disease. So this is prions in the brain. So these are proteins which clot together, which clump together and form bigger and bigger clumps, right? And so inhibit neurological processes. And this on the right, it is a kind of schematic of various earthquakes which occur in this eastern California region, and you can see that two of these earthquakes cluster to form another quake. So in this paper they have actually found a way to characterize the strength of these earthquakes. Okay, so but from a more academic point of view, usually aggregation has been studied since a long time, from the time of Smoluchowski in 1917 when he postulated a differential equation for the mass distribution of various clusters. This is the equation, and this holds true for arbitrary rates of collision. K of ij denotes the rate of collision. But then the thing is, it's not easy to really solve this equation. First of all, it gives only the typical mass distributions, that is on an average what does the system do. That is one thing, and even then it can be solved exactly only for very few collision rates or kernels, the constant kernel, sum kernel and product kernel. So there is a lack of results for atypical events also in aggregation. Atypical, when I say atypical, they are rare events. So the model, I'll just briefly go through the model. It's just that we start with m particles of unit mass, and in each collision a coagulation event occurs, an aggregation event occurs. So here this first bubble has m particles of mass 1, 1 plus 1 is 2, so that's what is shown here, and then you have particles of mass 1 and 1 particle of mass 2. So multiple collisions, either 1 plus 1 can go to 2 or 1 plus 2 can go to 3. So as the number of collisions increases, the number of possibilities also increases, right? And the number of clusters of course reduces by 1 after each collision, and in this whole process the total mass m is conserved. So the main question we are asking is this: if we just fix the initial condition and say that we are starting with m particles of mass 1 initially, the system will follow the pink line. So what I am plotting here is number of n of t, number of clusters with respect to time, okay, that follows a certain trajectory which is the pink trajectory. But now if I say that, okay, I want this capital N number of particles to remain after a given time, tau short or tau long, then it has to follow a different trajectory, right? So the question we are asking is, what is the probability of these other trajectories? So so now is there any systematic way to study rare events? So analytically, a very popular and concrete method is the large deviation theory. Numerically, there are a lot of methods available. The most common, I think, is importance sampling and its varieties, and also there are other splitting algorithms, various kinds of algorithms which have been used. We have used importance sampling, simple, So I'll start with large deviation theory. So this is a plot of the, it is a simple symmetric random walk, and this is the, okay. So what are we doing in large deviation theory? It's based on the fact that the tail probabilities of a distribution are exponentially small, and we have a rate function f of x, so, which that is in the limit of some large parameter n going to infinity, then this f of x goes as minus log p, the distribution, by n. This is what characterizes the rare event. It's called a large deviation rate function. In certain cases, it is also called the action. So this plot is of the rate function of the displacement of a symmetric random walker. The thing is, it's not always easy to find f of x. It's for a random walk, it can be done, but it's not always easy. And this is the f of x for a random walker. Importance sampling. So in this paper, Monte Carlo algorithm to measure probabilities of rare events in cluster-cluster aggregation, what we have done is to use importance sampling to benchmark using the constant kernel. That is, the quantity that we are plotting is probability of some rare event, right? So probability of n particles remaining at time t. So that we numerically develop an algorithm to numerically calculate this probability and also match it with the exact solution. So the constant kernel is the simplest kernel in aggregation, and for that we can find the exact solution for this quantity p of m and t, and we match these two and find that they are in agreement. The right side, the plot on the right side is the rate function f of x, and these two plots are again for the left hand side is for the constant kernel and the right hand side is for the sum kernel. It is possible to find the exact rate function or the action for the constant sum and the product kernels. I have not plotted the product kernel here because that is up to Nanda Devi, it's still running. Okay. So another thing to remember is this P of m and t, that is probability of n particles remaining at time t, also has a large deviation form for any arbitrary collision kernel. It may not always be possible to find what exactly that rate function is, as it is in the case of constant sum and product kernels, but it does have a large deviation form that we can see numerically. So the other results are that, so for the product kernel we see, so in the general Smoluchowski theory also, for a product kernel, after a certain time, tau equal to 1, there is a phase transition which occurs, that is, there is something called gelation, where all these masses coagulate together to form a gel-like structure, a macromolecule which kind of eats up all the other molecules or particles in the system. So that we see in our theory also, and we can characterize it using the rate function. And we have also been able to find the large deviation function for this process Ka going to La, which means that K particles just coagulate to form L particles. Thank you.
Thanks, Subashri, for this exciting talk. So questions?
So when you say it forms a gel-like structure, so do you see something like an Oswald ripening, that clusters are coming together and finally you see one cluster?
Yeah.
And then how do you actually physically characterize that it's, I mean, how do you know that it's gel-like?
So We know that. Okay, so in the large deviation function, what happens is that the second derivative of the large deviation function in our case shows a jump. So we don't see anything in the large deviation function itself. So that fooled us for quite a long time actually. The large deviation function itself doesn't show anything, but once we plot the second derivative, we see a huge jump at that point. I didn't show that here, but that happens even if we don't have this constraint, this final, even if I don't say that n particles should remain at time t. Even in the normal Smoluchowski case, it shows gelation.
Any more questions?
How is all this related to Varadhan's work?
Okay. So Varadhan's, so yes, I know, I do, but we don't, all we are saying is that we have the probability distribution follows a large deviation principle, satisfies a large deviation, hence there is a rate function. That is the basic building block of large deviation theory, and that is all we are saying. Yeah.
So, do you have any mechanism for clustering or any specific mechanism? How does this clustering happen?
That depends on the rates that we put in. The Kij, that is the rate. So I can say that Kij equal to 1 means that any particle, any cluster, any two clusters can coagulate with roughly equal probability.
I mean any microscopic mechanism that you don't have, right?
No, in this sense, no. Everything comes with only in the cluster, in the Kij.
Okay.
Yeah.
Thanks, Subashri.
Thank you.